SwayamPrabha. Digital India. Educated India.
We begin the week 9 lectures, and in this week we are going to discuss about inviscid high temperature non-equilibrium flow. The contents of this week would be recapitulation of vibrational and chemical non-equilibrium, which we have visited earlier, but since these are extremely important topics from the context of week 9, we are going to have a quick recapitulation of the same, followed by study of the distinction between equilibrium, frozen and non-equilibrium flow. Then we will move on to the governing equations for inviscid high temperature non-equilibrium flow, and finally, we would look at some applications including flow across normal and oblique shock, nozzle flow, blunt body flow, etc. Let us begin by looking at what circumstances are important for us to look at inviscid high temperature non-equilibrium flow. We would notice that for low densities, which may be occurring at high altitudes, and high velocities, which may be occurring for hypersonic cruise vehicles traveling at fairly large Mach numbers in the upper reaches of the atmosphere or entry into the Earth's atmosphere, the molecular vibrational energy exchanges as well as the chemical reaction rates occurring within a fluid element will fail to keep pace with the rapid flow changes which occur at such velocities. And you may recall that we have studied earlier about molecular collision rate Z, and that happened to be a function of pressure and temperature. And very briefly mentioning, this is an important functional relation that we discussed about, that it is directly proportional to pressure and inversely to the under root of temperature. And you may understand quite easily that low densities correlate well with low pressures, high velocities would correlate with large temperatures, and thereby you would see how the collision rate connects with pressure and temperature at such low density and high velocity situations. The consequence of this is that the distribution of molecules within the various molecular energy modes, the chemical reactions which are occurring at high velocities, high temperatures, and even the ionization of some species could be actually occurring at non-equilibrium conditions. Equilibrium flows, we studied the inviscid version of that in week 8, are going to remain identical no matter how large the body might be or how small. On the other hand, the non-equilibrium flow over a given body shape, it depends critically on the size of the vehicle. This is known as the scale effect, and that is a very dominant effect in non-equilibrium flows. Non-equilibrium effects are significantly enhanced for smaller bodies at higher altitudes, while equilibrium flows occur for larger bodies at low altitudes. So, this is a very important point that you need to keep in mind. Why are we interested to study the particle collisions? Because we are talking about vibrational rate equation. Over the next few slides, you will see that we will recap the vibrational rate equation. How is it going to be relevant for us in a study of hypersonic flows? Let us try to recall from an earlier slide that if the gas is stagnant, let us say it is not flowing into a hypersonic wind tunnel, or it is not flowing over a hypersonic vehicle during atmospheric entry, or it is not flowing into a rocket engine, Then in such a stagnant gas, if we allow sufficient time and we wait for all the particle collisions to take place, we will find that the gas would come to equilibrium. It will attain the equilibrium thermodynamic and chemical properties if allowed enough time, and this we had discussed earlier in week 5. However, when the gas is rapidly flowing through some device like a wind tunnel or a rocket engine, which are internal flows, or external flows across hypersonic vehicles, then the fluid elements of the gas might be carried far downstream of the device or of the vehicle, and before the necessary number of particle collisions could occur, so that the fluid elements could be at equilibrium, they are swept downstream. This creates a non-equilibrium situation. To deal with non-equilibrium flows like the ones mentioned above, we have to deal with the frequency of the particle collisions, and we also have to talk about the relaxation times which are involved. Of course, in this week we are going to talk about it from the inviscid perspective. In a later week we will bring in the viscous effects, and that is where you will find that the transport properties of the gas, namely the viscosity coefficient, thermal conductivity, diffusion coefficient, all would get altered under non-equilibrium situations. These properties are essentially affected by the mean distance a particle moves between one collision and the next, which is called the mean free path, which we have studied in kinetic theory of gases. And depending on how mean free path varies, how long do you allow the particles to engage in these collisions, so that the transport properties are at equilibrium, will really matter. We take some time to revise the vibrational rate equation now. In the kinetic theory of gases, we discussed about molecular collisions and that they are necessary to initiate chemical reactions. Similarly, if we want vibrational energy of a gas to change with time, it can be brought about through molecular collisions only. Therefore, molecular collisions play an extremely important role, whether we are talking about the vibrational energy exchanges or chemical reactions. When we try to find the time rate of change of vibrational energy of the molecules, we of course need a vibrational rate equation. At this point, we recall about the energy level diagrams that we have visited several times now, and the fact that vibrational energy level diagram indicates the quantized energy levels. We would concentrate our interest on the ith vibrational energy level, and we will look at particle collisions which can allow particles to move to and from that ith level, from and to the immediately neighboring energy levels, namely I minus 1 and I plus 1 respectively. Therefore, outward movements from I could go to either I minus 1 or I plus 1. Inward movements can be again between I minus 1 to I or I plus 1 to I. Having said that, once we account for the possible transitions from and to the ith energy level, we would end up getting a rate equation of this form, where it shows the time rate of change of the particle population at the ith energy level given by N I. And we find terms involving P with two subscripts. So, if we generally refer to it as P m comma n, it is the transition probability, which is the probability that a particle at mth energy level will jump to the nth energy level due to a collision with another particle. Z of course involves the collision frequency, the n's at the respective energy levels indicate the instantaneous population, and therefore, the first two terms account for the rate of increase of Ni, the next two for the rate of decrease of Ni, and consequently the difference between the two would decide whether the Ni increases or decreases with time. And further we include the vibrational rate constant given by k m comma n, and that is basically a collection of the probability and the frequency term, and consequently the master equation for vibrational relaxation boils down to this, where we have already indicated the collisions result in exchanges between only 3 energy levels. Now, from the master equation shown below, by using the Boltzmann equation and some concepts of statistical mechanics and thermodynamics, we can derive the final form of the vibrational rate equation. We had discussed it in detail in week 7. So, if you do not recall very well, you should go back to the week 7 lectures once again and revisit. Here we are going to do it very briefly. So, here comes the vibrational rate equation, which we had derived at that time in detail, and it is of course an ordinary differential equation that relates the time rate of change of instantaneous value of vibrational energy to the difference between the equilibrium value, which is this, that is being sought, and its instantaneous value without the superscript EQ. So, the one without the superscript value of course is the instantaneous value, and it also happens to be the local non-equilibrium value. It figures on the left hand side too, because that is the one which is varying with time. So, this is basically a time evolution equation. The tau term plays a very important role here, that is the vibrational relaxation time, and it depends on several parameters. Finally, it has a dependence on temperature, which is very evident from here. Additionally, if you bring in the role that Z plays there, you will find that it actually depends on pressure too. So, the K10 is the rate constant for transition from energy level I equal to 1 to I equal to 0, that is the ground level or 0 energy level, and the K10 can be further expressed in the form of a product of P10 and Z, where Z of course is proportional to P by under root T, which we have visited earlier also. It so happens that the denominator that we have over here as units of inverse of time. Let us try to analyze the behavior of this ODE, and we will cite some kind of a physical example here in order to perform that analysis. We consider a unit mass of the gas in equilibrium at a given temperature T, and then if it is at equilibrium, then we can equate the E vibrational with the equilibrium value of the E vibrational, and both of them should be equal to this expression, which we have talked about earlier from statistical mechanics. And we can clearly see that the energy is definitely a function of temperature from this expression. If we now instantaneously excite the vibrational energy mode of the gas above the equilibrium value that it is possessing by feeding adequate energy, one example of which could be passing a laser beam through the gas. Another example could be the localized heating of the flow due to the occurrence of a shock wave, and we have discussed about the theory of shocks in detail in the previous week. So, there could be different ways by which the excitation of the vibrational energy mode can actually happen. Then it will have a higher energy value at T equal to 0 when either the energy is fed or it gets heated up because of a mechanism like a shock, for example. And let us denote the excited energy level as the one with superscript capital E, where the capital E stands for excited. Obviously, it should be greater than the earlier level of the energy. So, at T equal to 0, here is the jump from the earlier level to a much higher level, and we are going to now follow the happenings over time. We have a sketch over here to indicate what might be going on as time passes. Let us try to do a little deeper analysis of the same. So, the excess energy that has now become available in the vibrational energy mode will spread to the translational and rotational energy modes as the excited particles collide with the unexcited ones and they exchange energy. So, the percolation of energy into the other modes of course happens through the energy exchange brought about by the collisions, and we assume here that the excitation is not so strong that it can affect the chemical reactions or electronic energy mode excitations. In that scenario, as the vibrational energy spreads to the other modes, especially relevant is the translational energy mode, then the temperature of the gas will definitely increase, because the translational mode clearly has a direct proportion with the absolute temperature. As the T increases, the equilibrium value of vibrational energy will also increase. This rise is indicated through the increase of the E vibrational value shown by the dashed curve. So, the rise from the earlier equilibrium value to a higher value, a gradual growth, a gradual increase in the temperature is basically brought about by the energy exchanges, which ultimately lead to the increase in temperature of the gas, and that is basically because the translational energy gains out of the collisions. The spread of the vibrational energy across other energy modes is reflected through the fall of the excited value shown by the solid curve, which is above. And interestingly, you find that both seem to be asymptotically moving towards an intermediate value, which will be a new equilibrium value for E, and that of course will take some time to happen, and that is basically the relaxation that we need to look at, the relaxation time we need to look at for the vibrational energy exchanges to take place. So, the dashed and the solid curve asymptotically merge to define a new level of vibrational energy. This happens after some time lapse, as can be seen from the plot, because it happens through molecular collisions which are governed by a collision frequency. We of course mentioned it already, but it is worth recapitulating again, and this is a very, very important concept. We will see that this kind of a relaxation mechanism works for different kinds of flow mechanisms or flow problems, like in the case of shocks, for example. When we look at flow behind a shock later on, you will find a similar mechanism working there. From the relaxation time equation stated earlier, we can see that the tau is of course a function of both pressure and temperature. Relaxation time is dependent on transition probability and collision frequency, and consequently the functional relationship becomes very clear. Transition probability depends on the relative kinetic energy between the colliding particles, and therefore, it is a function of T alone, while Z is a function of both P and T. Now, we very often look at modeling of the vibrational relaxation time. For most diatomic gases, the Landau-Teller rate model is what is often used, and it is going to functionally represent the dependence of tau on P and T through equation of this form, where P and T figures here respectively, and you find that the T resides within an exponential term. We also have some constants which may be varying from one situation to the other depending on the species we are talking about. If you take a natural log of this equation, it comes out in a linear form like this, which may be easier for us to plot. The C1 and C2 values are available from pure diatomic gas tables. They are experimentally obtained. They are difficult to obtain because these vibrational rate data have to be obtained from shock tube experiments, which are usually very short test duration experiments, typically running into few tens of microseconds, and therefore acquiring reliable data within such extremely short test durations is always very challenging, and the question further remains that how reliable are they. Therefore, extreme care needs to be taken to have reasonably reliable data. For example, for molecular oxygen, the two coefficients C1 and C2 have the values shown here. Note the units that we have over here. In the case of C1, it is atmosphere hyphen microsecond, while for C2 it is in Kelvin. Similarly, for molecular nitrogen, we have the values for C1 and C2 below, and these work over a fairly wide range of temperatures of around 800 Kelvin to 6000 Kelvin or so. There are of course certain limitations of the vibrational rate equation, which we need to briefly discuss now. The point number one is that it is only valid for diatomic molecules that are considered or conceptualized as harmonic oscillators, and for harmonic oscillators the epsilon vibration term shows as NH nu. It is valid only for harmonic oscillators, and harmonic oscillators do not follow this rule precisely. Secondly, in the master equation for vibrational relaxation, which we saw earlier, where we talk about the time rate of change of the population of the ith energy level, we have considered that quantum jumps of this form are only allowed between I and I plus 1 and between I and I minus 1 respectively, where we have used a left right double arrow sign to indicate jumps which can happen in forward as well as backward direction, which of course will mean that either the population decreases or increases due to such jumps at the energy level I, and also simultaneously at the other two participating energy levels I plus 1 and I minus 1 only. So, it is confined only to 3 energy levels essentially, and that is basically a kind of limitation of this equation. We did not consider multiple quantum jumps, we just confined to the single quantum jumps alone over here. What would the multiple quantum jumps look like? You would then allow jumps like I to I plus 2 and back and forth, similarly between I and I minus 2. Such jumps can however occur in anharmonic molecules. However, the associated transition probabilities are rather small. Now, having said that, since transition probabilities are small, you can say by and large the master equation that has been considered is going to be reasonably accurate for all kinds of diatomic gases. If we extend this idea of single quantum jump and multiple quantum jumps, it would be relevant to discuss about translational vibrational energy transfers, which we indicate as T hyphen V, as well as vibration energy transfers indicated by V hyphen V. Let us consider a diatomic molecule X Y comprised of one atom each of pure species X and Y respectively. It is not necessary that they have to be different, they could be identical also. The master equation mentioned earlier in 2 included only the translation vibration type energy level transitions, where when two molecules of X Y collide or interact with each other, where both of them are at the nth vibrational energy level, then one falls to a lower level while the other sustains, and because one of them falls to a lower energy level, therefore, there is some energy which is surplus now, which is released in the form of kinetic energy. So, collision between two XY molecules leads to one of the molecules losing vibrational energy and dropping to the lower level, and consequently leading to release of kinetic energy. The lost vibrational energy manifests as increase in kinetic energy, and therefore, it will end up increasing the translational energy content of the gas. Now, instead of one of those molecules falling down by one energy level to the n minus 1th energy level, if due to collision one of them went to the n plus 1th energy level, there would be decrease in the kinetic energy content of the gas overall, and therefore, decrease in the translational energy content of the gas in general. So, that could also happen in the case of a translation vibration energy interaction. Now, the master equation mentioned in 2 did not account for the vibration type energy level transitions. If we look at them, then 2 of the colliding molecules, if they are initially at the nth energy level, then we will find that one of them move up by one level while the other moves down, and therefore, one goes to the n plus 1th level, the other to the n minus 1th level, and this exactly happens the way we have indicated here for harmonic oscillators. There would be no kinetic energy surplus or deficit in the system. However, if it was an anharmonic oscillator, then we would see that though they move to the two energy levels respectively n plus 1 and n minus 1, there would be some kinetic energy interaction also accompanying those movements to two different energy levels. Either there is a surplus or a deficit, and that is what happens in the case of an anharmonic oscillator. The vibrational energy lost by one molecule is gained by another molecule exactly by the collision partner, is what we see in harmonic oscillators that we have mentioned over here. This is because for harmonic oscillators, the spacings between all energy levels are identical. They exactly follow this rule that the E vibrational is n h nu. So, if you use different integer values for n and you move up or move down one level each from a reference level, you can clearly understand that an interaction of this kind will end up producing no imbalance of energy. Therefore, the energy lost by one XY molecule is exactly gained by the other molecule, and no energy change occurs in the translational mode. So, if there was some energy change, that would have affected the translational mode. However, it does not happen because of the exact satisfaction of this condition. However, that is not the case for anharmonic oscillators, and because of the differences between different levels of energy which are adjacent to a reference energy level, therefore, there is a kinetic energy deficit or surplus which is available in the translational mode. In reality, all molecules are anharmonic oscillators, hence the energy level spacings are essentially unequal. They vary with n in the E vibration expression, if you look at it that way, and the consequence is that an anharmonic oscillator, there is a small amount of translational energy exchange if we have an anharmonic oscillator, which is indicated through the Ke term we have seen before. Thus, in cases where the VV type transitions are important, the master equation has to be modified to accommodate them. So, that is one of the lacuna that we had in the master equation, because we wanted to have it in a simple form, which is essentially catering to the TV type of transitions only. When VV type of transitions are important, we will see that that becomes a major issue where, say, a flow is expanding through a nozzle, it is leading to a decrease in the gas temperature in general because of the expansion, and VV type of transitions which occur in the anharmonic gas molecules at that time would end up leading to some kind of a overpopulation of some of the higher vibrational energy levels, and that is higher in comparison with the corresponding harmonic oscillator gas molecules. This is what is called as anharmonic pumping, and it is relevant in gas dynamic and chemical lasers. An opposite effect would be seen for anharmonic gas molecules when we compressed the medium. Let us conclude here. In this lecture, we discussed circumstances under which inviscid non-equilibrium flows can occur. We revisited the concepts associated with vibrational non-equilibrium and the vibrational rate equation. To explain the time dependence of the vibrational rate equation, an example was discussed, and finally, we looked at some of the limitations of the vibrational rate equation that we discussed. Thank you.